if I had my preference, those 70,000 people out at the stadium this last weekend, right? They would be there for y'all, right? We would be doing physics exam and there would be 70,000 people. How is he going to do? Okay, so let's try number 12 on the practice exam. 3 different potentials written down. A, B, and C. So one is for the particle in a box, one is for simple harmonic oscillator, and one is for the hydrogen atom. Which one is which? Label them for me.
One's for, like you said, spring, hydrogen atom, and
One is for a simple harmonic oscillator.
all right.
One is for a particle in a box, and one is for hydrogen atom. Boom, the cannon goes off, the cheerleaders start dancing, right? 10 points. Right? You're gonna do the push-ups. You're gonna do the push-ups, 10 push-ups, right? The answer starts up, right? Clemson's fielded a great physics team this year.
You have different universities, like
This is the way it should be, right? This is the kind of stuff that people, fans, the supporters of Clemson University should be cheering for, this kind of stuff, right? Don't you think? I mean, doesn't that make sense? Who cares whether we do big force? But it does matter that you guys are learning physics. That makes a lot of, that's what education is about. And this is really the hardcore part of education. Understanding the physical world. Really central to your being. So I'm quite serious. We need a physics class that the football team can be proud of. Well, I'm cheering for you guys when you're taking the tests. I really am. And we should get cheerleaders out here to do that for us.
You know, I've been both a football player and a physics student. I mean, they're both pretty fun, but there's just like one that's easier to watch.
Well, there's one that we watch for entertainment, right? We can relax our minds a little bit, just watch something that doesn't matter very much, but this matters. Okay, so number 13, for the same three problems, simple harmonic oscillator, hydrogen atom, particle in a box, identify the wave function. So I've written down 3 different wave functions. Would somebody like to, this is tough. Sure. This was ground state wave function, I think, right? Yeah. So, okay, pretty good. Anybody see a problem with what Mr. Patel wrote?
yeah, the L should be inside the argument of the sign.
Correct. Right?
Yeah.
Yep, right. So the L should be inside and it's ground state. So N should be 1 for the ground state. The probable request is ground state. Okay.
And it shouldn't be like a square root of 2 over L from the sign.
Yeah, so there's normalization on all of these. I'm not expecting you to memorize normalization, but how would you get the normalization? How do you find the constant on front? Yeah, you integrate psi squared and set that equal to 1. So for the simple harmonic oscillator, you would take this Gaussian. And then this ought to equal 1, that determines the constant. So you should be able to use the table of integrals that provided that for you and figure out what c squared needs to be so that this is 1. In this case, what would be the interval?
That right there, with base x of r.
No,
No?
no.
2.
Say again? Yeah, so there is going to be from 0 to infinity. R goes from 0 to infinity. And there's the angular part. So there's a c squared, and then there's 4 pi for the solid angle over the sphere. R squared e to the minus alpha r dr. So that's an integration over it's using the spherical coordinates. So Cartesian coordinates in 3 dimensions. We haven't done this. We didn't go over the integration in 3 dimensions, but instead the volume in spherical coordinates looks like that. And when you integrate over the theta and the pi, you get 4 pi. And then the rest of it is this. So this is equal to 1. We haven't done this, so I wouldn't expect that you would know this, but that's how. In principle, you determine the constant by squaring the wave function, integrating over the volume.
And solving for the constant from there.
Yeah. And this one then, the wave function is 0 outside the box. So now the integral is just from 0 to L sine squared pi x over L.
C squared, is that?
Yeah.
As in the speed of light.
No, as in the constant here.
Ah.
Constant, whatever that constant is. You square the wave function, you get the square of that constant. And then the total probability has to be equal to 1. So that determines what this constant has to be. So this one, C will be square root 2 over L. For that one. Remember that one. Okay. Okay, so he didn't get the point after. Did pretty good though. All right, so let's see here. The last one, matching. Identify the appropriate dependence of the energy eigenvalue on the principal quantum number. So in each one of these cases, there's a principal quantum number. So how does the energy for the simple harmonic oscillator depend on the principal quantum number, the atom, and the particle in the box? Somebody write down what those are. Let's see, you've done one. Somebody who hasn't had a chance yet.
Maynard hasn't done.
These are just recalling. I certainly don't expect you to derive these, but I do expect you to remember.
I'll give it a shot, but I don't think I'm right.
All right, give it a shot. Yeah, you were right, but you're not right. All right, good guess. Thank you for playing. No score. Got 3 and out. How about what would be the correct answer?
It would be because that's with respect to the first the ground state. So you multiply. So E sub n will be n squared E1.
This would be one Rydberg here. But these are not correct. They're not, don't have the right association. All these 3 are correct, the list, but they're not associated correctly with it.
Top one will be going to PIV.
Particle in a box, right? The energy goes like n squared to the particle in a box.
And
I'm sorry. Somebody else.
The second one.
Simple harmonic oscillator, right? Very unusual dependence here. The spectrum of energy levels in the simple harmonic oscillator is evenly spaced all the way up to infinity. There's no upper limit. And so this is the hydrogen end. Spectrum goes like 1 over n squared to the hydrogen end. N is equal to 0, 1, 2, 3, 4, and so forth for the simple harmonic oscillator. It starts 0 for the simple harmonic oscillator, but it starts with 1 for these two. 0, 1. It's just conventional that we start numbering a little bit differently in the different cases. Yes, sir.
For Rosberg's constant, it's positive or negative?
The energy is negative.
And is that because,
That's a good question. Why are the energies for the hydrogen atoms, the energies are all negative? Whereas for the particle in a box and the simple harmonic oscillator, the energies are positive.
Because we set the 0 point at infinity.
Very good. This isn't, they're all bound states. The difference is where you set the zero, the reference. For the hydrogen atom, the reference is when the electron is pulled infinitely far away from the proton. So if you draw the potential energy for the hydrogen atom, it looks like this. This is minus g squared over r. So the zero is out here, and the bound states are all below that zero. So that's why for the hydrogen atom, the energies are all less than zero. For the simple harmonic oscillator, the potential is 1/2 kx squared. Here's the zero down here at the bottom. That means that the spring, in the case of the mass on the spring, it means the spring is not stretched at all. It's at the equilibrium point. Potential is positive either way. Whether you compress the spring or stretch the spring, the potential is going up. And so the reference is here, and so the energies are all going to be greater than to the left. And the particle in the box, the zero is the potential in the box. The particle is going to be some energy above. So that's why the difference. Does that make sense?
so we can have negative energy along with the potential energy is negative.
Sure.
And so that's not, okay,
Right? So what does the negative potential energy mean? It means that if I let the electron, I'm starting off way out here, there's an attractive force. It's very weak if I'm far away, but it's attracting, pulling the electron in. If I let the electron move in, then the electrostatic attraction is doing work, positive work, because the displacement's in the direction of the force. So that results, that means the potential energy is going down. In other words, if it's going in the direction of the force, it's going downhill in potential energy, right? Remember the general relationship between the force and the negative potential, energy, the gradient, the derivative with respect to x or r, whatever it is. The force is downhill in the direction of lower potential energy. So here the force is inward, and as the electron moves in, potential energy is going down. It's gaining kinetic energy, if you just let it go, it'll start gaining kinetic energy. The total energy is conserved. These are all conservative forces. So if the kinetic energy is increasing, potential energy has to decrease. It's going downhill.
the total energy from the very beginning has zero. It has zero to this. That means it's
If it
zero.
starts off at rest, some far away, some distance way out here, the total energy is almost zero. Just a little bit less than zero.
Oh, it won't be negative.
Yeah, a little bit less than zero.
A little bit less. That's all.
Yeah. Okay, any questions about those?
I'm a little confused about why sometimes the quantum numbers start at 0 and sometimes they start at
Don't be confused by it, it's just choice, right? What we need here is I mean, you could choose to start it at 0 in all cases or 1 in all cases. It would change how the energy depends on n in that case. It's purely conventional. And, you know, if we were wanting to be consistent everywhere, we might have chosen it differently. So it's purely conventional.
Rydberg constant. Rydberg constant. That's not like the ground state for the hydrogen atom.
Sure it is, yeah.
You just
If I
get-
said in the one, the energy of the 1s state is -1 Rydberg. The Rydberg is 13.6 electron volts. So the first state, so 1s is here, so that's negative 13.6. The 2s would then be 1/4 of that, so it'd be up here. 3s would be 1/9. Okay, and then it keeps it. So there are more and more levels. There are an infinite number of levels between here and 0. Infinite number of bound states in a hydrogen atom. Infinite number of bound states here because potential just keeps going up. There's no way it can get out of this well. It's infinite. It just keeps going up. There's no limit. Particle in a box, there are an infinite number of states because the walls are infinitely hard. So these are not particularly realistic situations. That is, the harmonic oscillator and the particle in the box are rather extreme. You don't find situations like that with the hydrogen atom. It's definitely a real concrete case. Okay, any questions? So you should be able to recognize potential energies, wave functions, energy eigenvalues, and associate them with these 3 concrete problems that we've done. So simple harmonic oscillator, hydrogen atom, particle in a box. You'd have those memorized so that you can relate. Okay. Question? How about the particle in the square and particle in the box and a particle in a cube? So first, let's need to recall all of the states for a particle in a box. Here's the particle in a box. There's the potential. We said the energy spectrum goes like n squared times something. What is the wave function? The time independent part. Stationary, the pure mode solution. What does it look like? Say again?
Is this for particle in a box or for like the
Particle in a box.
Oh, it's the square root of 2L sine.
And here's the end. Okay. And what is the energy of that? I squared over 2mL squared, which you get by substituting this into the Schrodinger equation for a particle in a box. Right. So inside the box, this is the equation. And these are solutions to this equation that match the boundary condition. Remember, the boundary conditions, wave function has to vanish from the ends. Okay, and then you substitute this into here, and you find this. Okay, so you should have this memorized. Okay, so having started with this is the particle in the box, what is the particle in a square and a particle in a cube?
Isn't there an h bar squared on E in the EM?
Thank you. Yeah, h bar squared. There we go. Thank you. Yeah, there's not an h bar somewhere. I've done something wrong, right? Because the energies are always going to involve h bar because it's in the Schrodinger equation. Okay, so who can construct just by particle in a square, particle in a cube?
Well, like
Use the separation of variables for the wave function.
Right? You do it by separation of variables. So I'm asking you just to get to the bottom line. You just, it's not really very hard. Can you write it down for me? The
Separation.
well, just write down the wave functions and the energies. So the square has side L.
So I'm gonna start with like
No, you don't need to do that. I just want the wave functions and the energies. Yeah, I'm not asking you to work the whole problem out. I'm just asking what it comes to.
Oh, wait, actually, it's the same L for
It's a
everything.
square.
I forgot, yeah, I confused it with
That's
the
fine, you were
rectangle.
doing it for journal or rectangle.
Energies. Yeah, let's do that, right?
Yeah, there's two different ends now. Writing the total energy?
This is just like for the first end.
Okay, so
I
you're
know
E1,
like,
right.
for E and X.
There you go.
Yes, E1 and. The X plus Y squared is it M squared?
Yeah, good question. He's gotten a good, see what his question is it nx plus ny squared or nx squared plus ny squared?
Well, it's just gonna be nx squared. Not nx plus ny squared, because you're looking at just the energy of the x.
Now we're looking at the total energy.
Well, that's the total, that looks like E sub n x.
Yeah, this is a
Oh.
function of both nx and ny.
That's lucky. Yeah.
It's NX squared plus NY squared.
Yes,
Yeah.
sir. And how do you remember that?
I just remember seeing it.
Okay. Well, if you think about it, your argument about the separation of variables is good. So there's going to be a separation constant for each direction, right? And then if you had it in x plus ny squared, there wouldn't be a separation constant. These are separated. There's an energy for the x direction, energy for the y direction. If you had it in x plus ny squared, it would be a term nx times ny. It wouldn't be a separation. That makes sense? Yeah, good. Okay, so how about the particle in the cube? It's very simple, using this as a model. There are three quantum numbers, nx, ny, and z. And what's the energy? This E1 nx squared plus ny squared plus nz squared. Right? So if you don't have that really down in your memory and to recall, go back and work the problem. Work the particle in the square first, using the separation of variables. That's what it should lead you. Okay. Okay, let's go look at the simple harmonic oscillator. So who can write down the time independent Schrodinger equation for the simple harmonic oscillator? I want TISE or SHO. All those stand for. In one dimension. This is in one dimension. Do it. There is definitely going to be some question on the test where I ask you to write down the time independent Schrodinger equation for some problem. It's definitely going to be on there.
I mean, it would just be the same thing with the potentials.
Go ahead. He's our star receiver today.
You know,
What
I
position did you play?
was the starting receiver.
Yeah.
I can't catch. I should have been a running back or something.
You got a catch now. You're a running back today. These days. Very good. That's it. So the potential, this different time independent Schrodinger equations will be different from each other only in this term here, whatever the potential is times the wave function. That's how they'll be different from each other. Okay. Okay, so I'm on to the question here is to show that this is a solution. Show by direct substitution. That this is a solution. And in the process, you'll find alpha, and you'll also find the energy on those two things. Well, if you know the spectrum, and if you know, this is not the ground state wave function. This is the first excited state wave function with a constant determined by integration. So you should get 3 halves h bar omega. Oh, and how does omega relate to the constants here? Omega 0. It's the frequency of the simple harmonic oscillator thing that we got from mechanics first semester. Okay, who can do this? What do I mean by direct substitution? Just plug
Okay.
it in. So you need to take 2 derivatives of that wave function.
Yeah, just solve for K, plug that in, and
Now let's see how it goes.
yeah, if you want someone to come up and do it.
Yeah, I want somebody to come up and do it.
I could try.
Go ahead.
I believe in you.
Good. Let's simplify that a little bit before you go. That is a polynomial times the Gauss. There you go. Good. Okay, we can do the next one. Right, did you get this? Right, you need to be able to do this. Just apply the chain rule. Derivative of a product, so you have 2 terms. The derivative of x just gives 1, and then the derivative of the Gaussian gives that minus 2 alpha x. Come on, Mr. Green, you can do it. Of course, come on. Write it as a polynomial times the Gaussian. That's fine. Yeah, because we're gonna substitute it in the equation, so all the terms will have a Gaussian. So, okay, if you're rusty at this, practice it because it's gonna be on something like this at this level. You need to look for, gotta have the calculus down. You can't really understand modern physics without understanding the math. It's essential to the core of modern physics. So you've got to be able to take derivatives. Can't understand the Schrodinger equation unless you understand that derivative. Okay, so we substitute these terms in, so we have, that's the left-hand side. E times the wave function, then we have minus h bar squared over 2m times the second derivative. We have 1/2 kx squared times the wave function. So there's already an x out in front of the wave function. So all the terms have the Gaussian, so we can factor that out. So remember what this equation means. This is a function on the left-hand side is equal to a function on the right-hand side. The functions have to match. So you could do the following: cancel the exponential, the Gaussian. That's common to all the sides, all the terms. Okay, so that leaves us with
Should be same thing for X as well. Make it slightly cleaner.
you could do it for x, yeah. X is a common term. Thank you. That's fine. So you could cancel the x as long as you're not looking at the x equals to 0. So you're looking at this alpha squared h bar squared x squared here plus h bar squared over 2m times 6 alpha. So that's constant then, and then we have finally 1/2 kx squared. So this is a constant. The right-hand side is a parabola. We can collect the coefficients of x squared. So this is a constant is equal to a parabola. The only way for that to happen is if the coefficient of x squared vanishes. Does that make sense? These two things have to equal for all values of x. So this has to be 0. That gives us what alpha is. So that's the alpha in the wave function. It has to be that. That's the only way it can be a solution to the Schrodinger equation. See how we got that?
You're saying that X must equal 0.
No. I'm saying the coefficient of x squared must be 0. This thing in parentheses.
Oh, for all X. Oh,
For all X.
there you go.
Otherwise, this is a parabola, but this is a constant. So only way for the two sides to equal each other is for this term, the thing that's in parentheses here, to vanish. Set that to 0. That's what I did here, and then solve for alpha. This, I think for homework you did this. I think you did the ground state, first excited, maybe the second excited. This is straight from the homework. On a real test, I might not be inclined to do a first excited. I might just let you do the ground state, but you need to be able to do this. Okay, and alpha will come out to be the same even for the ground state. Okay, so now we have alpha. And so now we also have the energy. E is equal to 3 h bar squared over m times alpha, which is square root of 1/4 am h bar squared. And so square root of 1/4 is a half, 3 halves. We have an h bar squared here, the square root of h bar squared. So we have just an h bar. And then we have a m out here and the square root of km, so this is k over m. And so this is a u 3 halves h bar omega naught. Omega naught of that. Okay? Get the general idea. You're not actually solving the differential equation, you're just confirming. This is a solution, but you can see why the values of the constants come out the way they are. The value of alpha and the value for E come out to be these values. You're looking a little puzzled. Some of you are. Pensive may be a better word to apply. So
That's where it can't be, yeah.
okay. Question?
And this somehow, this confirms the, how this, confirms the,
You're confirming that wave function is a solution with a corresponding energy eigenvalue. Yes.
So in 3 dimensions, it would be x squared plus 3c squared.
Yes. And for the potential energy.
Can we just substitute similar to the solution that we just had?
Very good. Yeah. You do a simple harmonic oscillator in 2 dimensions or 3 dimensions. It's very similar to what we just did for the particle in a box, in a square, and a cube. All right, so if I'll assign that as extra credit if you'd like to work this out. In the same way that we did the particle in a box, a square, a cube, you can do the simple harmonic oscillator in 1, 2, and 3 dimensions. And there's going to be 3 quantum numbers, just like there were 3 for the particle in a cube. There's an nx, an ny, and an z, similar to this. You can almost guess what the energy for a 3-dimensional simple harmonic oscillator looks like.
And do you just want the like answers like we wrote on the board for the particle in a box, or do you want the whole shebang?
No, I won't ask you to do that, but so this is extra credit. Yeah, just guess it.
he wants to guess it.
Yeah.
He wants to actually solve for it.
Well, you can demonstrate it's a solution if you like.
So you want to guess.
This is so simple though, right? I mean, just using the particle in the box as a model,
Yeah.
going to
or
1,
guess
2,
would
3
be-
dimensions, it works for this problem too. Okay, let's see, demonstrate.
Guess the solution.
Yeah, I want you to guess the solution, and you can demonstrate that it works. Okay, who can demonstrate the commutator between x and p from the definition of p hat?
Here you
Do
go.
it. Go ahead.
That's very, very good or not. And the Crayola, yeah, the Crayola is terrible.
So that, explain that notation there. Right. Well, that's, yeah. that's a subscript, that X is a subscript on the del. Not clear the way you wrote it, that's supposed to be a subscript. Make sure your subscripts fall below the line, otherwise it doesn't look like a subscript.
It's so much cleaner when you write that way. It makes things much.
Okay, but not everybody knows what it means.
I apologize.
Okay, go ahead.
That's- it's just, It's in context of showing your equation, right? Like, that's not good. Must make a mistake somewhere. I want to say this guy, I want to say.
Take it down here.
Oh, there's X. There's an X there. That's the be an X here. This is gonna go away. Good.
Oh, what he did?
I can make it more clear.
The only thing I would quibble is this notation here makes it look like there's nothing off to the right. Remember, this is an operator relationship. And what's implied is that's acting on a function. And so you may want to put a function in just as a placeholder. So this acting on some function. This kind of implies that there's nothing over here to the right, so that's why I didn't like this. Just leave it like this. But then you have to remember that there's gonna multiply. This is gonna be operating from the right. Gonna operate on a function here. So there's gonna be an x, the derivative is going to act on x times the function. And then the derivative of the product of x with f has two terms. First, the derivative of x is just an f here. And the derivative of x on f. These two terms cancel. H bar f. Okay, so now we can still write this then in the more abstract notation, we're just understood to be a function that's acting on. The commutator is then just a constant. So when you act on some function with the commutator, you'll just get back a constant times that function. Okay, so using this relation, find what is it, x squared p. Somebody other than that?
That's one where you use like.
Good way to start your Thanksgiving break.
Didn't we do this in the homework where you like plug it in?
Yep, we did it in the homework. All of this stuff we did in the homework.
Good.
I don't think I've asked any question here that wasn't on the homework first.
Nah.
One of them was like, he's really excited. Can't wait to do it.
I don't know.
I don't understand why no one's like jumping at the scenes to do this.
He's squirming in a seat. You have to walk
I can do it.
Need to walk up.
Walk up.
and right on the board.
Oh, man.
And then I have to pick up the chop.
Yeah.
Oh,
The chop.
Yeah.
Man.
Are you the kind of guys who text your friends? Not just
yeah.
text them? I don't want to have to breathe in and out, call them and talk.
Actually, yesterday I called my friend. Yesterday I called my friend to ask him like text. I called my friend to ask him if he had a plan, but I could have texted him, but I didn't feel like typing it out.
Oh, that's even too much.
Since you could like do IH for it. I might actually just have to do it the long way with the function just to.
So are you about to work out all those derivatives and stuff again?
No,
Good, okay, because you can use this.
I remember, yeah, I know you can use that, but I'm just trying to remember where you used it. It was. And my memory's crap.
Why don't you write down the meaning of this? Write it down, expand out that commutator.
Oh yeah, now I remember. Yeah, I remember. It's like. Oh yeah, you try to switch it around.
Yeah.
So you did something like.
Yeah. That's it. Now you got it. Okay.
So that means you can do something like.
Mhm.
Well, okay, yeah, that's. I can still keep it here. I take a lot of time on my homework.
You want to change that?
Yeah.
Because you're changing the first term. Leave that one the way it is. Oops.
I did something, I must have done something wrong.
You did really well up to that point. What is XPX is not.
Oh, yeah, it's XPX.
You swap them without intending to, right? You don't swap.
Yeah, because it's an operator, it doesn't work like that.
Right. You see where this occurs now in your expression? XP.
Oh, yeah.
Right there, the left-hand side of that.
My memory was.
Well, it's something you need to practice, so that's a good thing to practice for the test, right? So he has this x squared on the left-hand side of p, and over here x squared is on the right-hand side. So you want to push the x through the p. That's the way I think about it. So we got to push both x's through the p. So he wrote it out here. He's got an xp. Then he substitutes this, which you get directly from the commutator. And then expand it out, but don't put this x, it's still on the left. This x is still on the left of p. This one's on the right now, so we have an xpx. But you can group them. The operator algebra is associative. You can associate like this, and now this xp can be expressed this way. Now the x is on the right-hand side. So you get another I bar x, and then you get a pxx, which cancels this pxx. Good job. Okay, so have a good Thanksgiving. Drive carefully. Take time to study. Come back ready for the test on Monday.